This video is brought to you by mywayteaching.com.
In this part, we are going to discuss about one of the important concept that is kinetic theory of an ideal gas. Kinetic theory of gases, it mainly depends on molecular picture, which means molecular structure. A given amount of gas is a collection of large number of molecules, isn't it? That are incessant random motion. Those molecules, or we can say the collection of molecules, will be in random motion. At ordinary pressure and temperature, the average distance between molecules is a factor of 10 or more than the typical size of molecule. Means it can be more than 2 angstrom, or it usually it will be in the order of 10. The in okay, in an average case, the distance between the molecules. Okay, thus the interaction between the molecules is negligible because the distance is quite large compared to liquids and solids, isn't it? And we can assume that they move freely in straight lines according to Newton's first law. However, occasionally they come close to each other and even they experience intermolecular forces. Only occasionally they come closer and even they experience this intermolecular forces. Okay, and their velocities change. These interactions, we call them as collisions. When they collide, the velocity will change. The molecules collide instantly against each other or with the walls and they change their velocities. These collisions, they are considered to be elastic. Okay, they are called as elastic collision. So we just begin with the idea that molecules of a gas are in incessant random motion, colliding against one another and with the walls of the container. That collision takes place, and all collisions between molecules among themselves or between molecules and the walls are elastic. So this is the basic idea of this kinetic theory. Okay, these all the molecules of the gas are in random motion, that too incessant random motion. Okay, this is incessant random motion. And when the collision takes place between the molecules and when the collision takes place between the molecules and the walls, those collisions are elastic collisions. So these are all the basic concepts of kinetic theory. Okay, now let us study what is this pressure of an ideal gas. Okay, you just consider a gas which is enclosed in a cube of side L. So as you can see, you just consider a cube of side L. Okay, this is X, this is Y, and and you just take the axis which is parallel to the sides of the cube. Okay, like here I have taken x-axis and y-axis. As shown in this figure, a molecule with velocity vx, vy, vz. This is the molecule with the velocity vx, vy, and vz, and there is another molecule with the velocity minus vx, vy, and vz. Okay, hits the planar wall, isn't it? This molecule hits the planar wall which is parallel to yz plane of area A is equal to L square. Since this collision is elastic, the molecule rebounds with the same velocity in y and z components. Okay, you can see this is the rebounded molecule. Okay, with components of velocity do not change in the collision, but the x component reverses sign. That is, velocity after collision will be minus vx comma vy comma vz. The change in momentum of the molecule is given by the change in the momentum of the molecule is given by minus mvx minus mvx, that is given by minus 2 mvx. Okay, by the principle of conservation of momentum, the momentum imparted to the wall during the collision is, yes, during the collision the momentum imparted is 2 mvx. Okay, to calculate the force on the wall, we need to calculate the momentum imparted to the wall per unit time, isn't it? So, in a small time interval delta t, a molecule with x component of velocity, that is nothing but vx, it will hit the wall if it is within the distance vx into delta t from the wall. That is, all the molecules within the volume a vx delta t only can hit the wall in the time interval delta t, isn't it? So, on an average, half of these are moving towards the wall and the other half are moving away from the wall. Thus, the number of molecules with velocity vx, vy, vz hitting the wall in time delta t is nothing but half a vx into delta t. Okay, delta t into n, where this n is the number of molecules per unit volume. Okay, the total momentum transferred to the wall by these molecules in time delta t, okay, is given by q is equal to 2 mvx into 1 by 2 a vxn into delta t. Okay, the force on the wall is the rate of momentum transfer, that is q by delta t, and pressure is force per unit area. So that pressure is given by, we know what is Q. So all the molecules in a gas do not have the same velocity. There is a distribution in velocities. Okay. So this equation, it stands for pressure due to group of molecules with speed Vx in the x direction, and N stands for the number density of that group of molecules. Okay. And the total pressure is caused, or the total pressure is obtained by summing over the contribution due to all groups. This is about single. When we consider all group, we get the total pressure, isn't it? And now the gas is isotropic, that is, there is no preferred direction of velocity of the molecules in the vessel. So by symmetry, we can write Vx square, that is the total Vy square is equal to Vz square, isn't it? So we get 1 by 3 Vx square Vy square plus Vz square, that is equal to 1 by 3 V bar square, where V is the speed and this V bar square, it represents the mean of the squared speed. And if you express pressure, that is given by 1 by 3 N M into square. Okay. So here about this derivation, there are some remarks that we should know. First, though we choose the container to be a cube, the shape of the vessel really it is immaterial. For a vessel of any shape, arbitrary shape, we can always choose a small, that is infinitely small area, and carry through the steps what we did now. Okay, that is not a problem if it is not in the cube. And both A and delta T do not appear in the final result. By Pascal's law, pressure in one portion of the gas in equilibrium is same as anywhere else. And second, we have ignored any collisions in the derivation. There, no, we have considered zero collisions while deriving. Though this assumption is very difficult to justify rigorously because collisions are common, we can qualitatively see that it will not lead to erroneous results. And the number of molecules which are hitting the wall in delta T was found to be how much? Yes, it is found to be 1 by 2 n a vx into delta t, isn't it? So now the collision are random and the gas is in a steady state. Thus, if a molecule with velocity vx by vz acquires a different velocity due to collision with some molecule, there will always be some other molecule with a different initial velocity which after a collision acquires the velocity like vx, vy, vz. If this were not so, the distribution of velocity would not remain steady. Okay. And in any case, if we are finding that the mean squared speed in x, that is vx bar square, on the whole molecular collisions will not affect the calculation. Okay.